Okay, well, good afternoon. Welcome to the second of the live afternoon invited talks. And it's a great pleasure to introduce my former graduate student, Randy Ewalt, who worked with Pekko Hosoi and I at MIT for 5 years from 2004 to 2009. After completing his PhD, he went to a postdoc with Chris McCosco for 2 years and got very interested in design. And so the inverse question, which is very different than we normally ask, where it's like, I have a fluid, what are its properties? He started to ask questions like, if I want these properties, what kind of fluid should I have? And that's what he's going to talk about this afternoon. But before I do that, let me just give you a very quick history. After his postdoc, he went to the University of Illinois, Urbana-Champaign, and won in 2014 the Metzner Award from the Society of Rheology for a young rheologist. He also won an NSF Career Award, and then the Pi Tau Sigma Gold Medal from ASME in 2015. And in 2017, his career award was turned into a PCASE award from the NSF. So he's had a very illustrious career so far, and he's going to tell you some of his thoughts today of the work with his group on designing complex fluids. Over to you, Randy.
Great. Gareth, thanks for the very kind introduction and spending time here helping to back me up on any technical difficulties as we've been seeing here. Anyway, right, so thank you all for joining as well, and thanks to the overall DFD program committee for the nomination and considering and accepting me as an invited speaker here. Thanks for your time. So designing complex fluids. Let me show a video of one example of a complex fluid. This is water in the front and a green gel in the back. And even before I show you rheological measurements, you already know with your eyes that the back gel is complex. It flows like a fluid at the higher stress loading, and it doesn't flow very much at all under the lower gravitational stresses. And when I say complex fluids, this is what I have in mind. To put it in the context of fluid mechanics, here's our wonderful momentum equation applied to a continuum. And where some of us like to think about complexity of velocity fields, I tend to think a little more about complexity of the stress tensor and what the constitutive behavior should be for that tensor. And I'll be living in the world of non-Newtonian constitutive behavior there, usually isotropic, incompressible fluids. When I talk about design, here are a couple keywords on what I mean by that. We all know people who maybe are in different fields using the word design to mean web design, or maybe engineering design is closer to what we would see at the DFD. But it really, of course, means to create something or even to make a plan to create something. Of course, if you want to design the rheological complexity, it's a huge open landscape, and one small step away from Newtonian behavior just creates an explosion of the ways to be complicated. On this next slide, I share with you what I learned from Chris McCosco in his book, published in 1994, on the 4 key phenomena of rheology. Of course, there are even more than this, but these are 4 important ways that fluids become complex. The first is viscoelasticity, or time dependence. The second one is shear thinning. That's the most common one you might see at a conference like this, and maybe the one you were first introduced to when you were learning fluid mechanics. But there are others. Extensional thickening is shown with the red liquid there, which self-empties, and the rod climbing, which is the generation of normal stresses, even though the flow is primarily shear. I say that shear thinning is what many of us are introduced to early on, because even in wonderful books authored by people like Ronald Panton, who's in our community, the figure that's used in his chapter on non-Newtonian liquids is exactly the shear thinning idea. He acknowledges, of course, that there are many other ways to be non-Newtonian, but you have to go to other books to see that. And again, we have many people in our community that have written extensively on this. And I show a couple here, Dan Joseph, Bob Bird, Bob Armstrong, Ola Hassiger, who've written works here that focus on the continuum level of complexity, and some more recently by names who are also very active in the DFD, Elizabeth Guazelli, Jeff Morris, Mike Graham, writing books that tend to focus a little more on microstructural ideas and where these properties really come from. So we have all this complexity, and I want to talk about design. I'll say one more comment that in fluid mechanics, we try to design and control things in many different ways. You'll often see us controlling flows by changing the boundary conditions, though. That might be changing the shape of the boundary, or if you imagine a little swimming microorganism, it's optimizing maybe the kinematics of the stroke. Even traditionally in the world of non-Newtonian fluids, we often just take for granted that we may have a situation where the fluid is non-Newtonian. Take these microswimmers, for example, in a biological context. Or even in the historical area of polymer processing, we just take for granted that things are complex and we want to deal with them. But the spirit of my work today is to really think about controlling those properties to achieve some diverse objective. And in fact, there are many diverse objectives that you can achieve by making the fluid complex in this way. I'll give a few examples with the pictures on the following slides. In the world of healthcare, of course, our bodies are made of complex, soft, squishy materials, but people who design injectable hydrogels have to think about the rheology, and making it non-Newtonian, for example, helps a hydrogel laden with cells actually stay in place after it's injected, just like the video I showed on my title slide. In the world of energy, getting much larger scale, this is a little, putting clip art on top of a real photo to indicate that the large structure in the bottom left is a large scale, grid scale energy storage with electrochemical batteries known as flow batteries. In this case, it's taking it up from a photovoltaic wind farm or photovoltaic farm. The fluids used in those flow batteries get very complex. They may be composed of polymers, colloids, and there's some wonderful design trade-offs to consider when formulating that. For the environment, it turns out you can put out fires better with complex fluids, whether they're gels or foams in other cases. And soft robotics, anything inspired by biology, of course, easily touches on soft matter and complex fluids. Historically, though, complex fluids were really driven by polymer processing in the world of manufacturing. Today, that's still happening, and there are lots of efforts on trying to make sustainable, recyclable polymeric systems, but also lots of work in additive manufacturing or 3D printing. And the video I'm showing on the upper left is one demonstration of how making a fluid non-Newtonian allows it to retain its shape after it comes out of the nozzle so that you can build up a structure. This will be part of the topic of the talk today. But you see this also in adhesives and coatings, where you may want to design these fluids to be shear thinning, but also viscoelastic. You see this in foods. I won't talk too much about this today, but this is my student, former student R.F. Nelson, blowing a bubble to demonstrate the rheological complexity. And you can have a lot of fun in this space too. So for example, this is a picture of hot ice cream that we made. This ice cream melts when it cools down, and it's a solid when it's hot. We make that out of methyl cellulose, kind of a playful thing. Speaking of playful, RF is also an amateur magician, and here are two magic tricks that work because of rheological complexity. The first on the left is something called Mystic Smoke. I have Tad Truscott, who's in the DFD, to thank for mentioning this to me, and then I shared this with RF. It works because it's a liquid that looks like smoke when you quickly open up your thumb and forefinger. But it works because it has a yield stress. It has this dramatic shear thinning so that it can retain its shape when it makes those fibrillar structures. And on the right, octopalm acting like an adhesive. So there's lots of opportunity to do something cool. And that's what brings me to this design thinking. As Gareth mentioned in the introduction, a lot of scientific work naturally starts by defining your problem statement in what material you have or what fluid you have, and asking what properties result and how might I be able to use it. I would use the word analysis there. This is taking language from the design research discipline. They contrast design with analysis, going in opposite directions. Of course, design in engineering is built on analysis and an understanding of cause and effect and conceptual and quantitative models for how things work. I like to break the world up in the following way. If I have some performance objective, like the direct write 3D printing, for example, I might ask what type of properties are actually important to make that happen. That's this top level. This is very much in the world of continuum-level fluid physics. And it's really valuable if you can ask those questions without needing to say anything about the structure, because you may desire certain properties independent of how you achieve them. This is a typical way of framing any design problem. Try to state clearly what your objective is, independent of your approach to achieving it. But the second level is also fluid physics, but it's at a smaller scale to understand where those properties come from. And the design framing tends to have us comparing and contrasting across many diverse material systems to achieve a particular rheology. And that way of thinking was motivating us to write this recent review paper. RF is the first author here. This is in collaboration with several of my colleagues here at Illinois and Jan Vermont, who is at ETH Zurich, who hosted my sabbatical there back in 2018. And what was really fun about putting this together is to make this comparison of how to achieve shear thinning and especially a yield stress fluid with a diverse range of material structures. So you start a little bit like a cookbook. How many ways can I bake a loaf of bread? How many ways can I get a yield stress? And there are, of course, many ways to do it. And the mathematical part of our mind says, okay, that's fine, but I'd like some equations to try to be predictive of these properties. And these do exist. Here, we're collecting a huge range of scaling laws. That's really the level of our understanding in many of these systems to understand how a property, in this case, the yield stress, increases as a function of formulation properties. So you see things like the volume fraction, which is this phi, or the energy of interaction between colloids in a particulate gel, or here A is the radius of those colloids. You see many of these are missing numerical front factors. In rare cases, there are numerical front factors, but many of them are just scaling laws. Yet these are still good for design. And this is something that would help to inform the design process to see these different systems compared against each other, whereas most of the primary literature, of course, focuses on one of these systems to try to figure out what that equation is. So that's what results when you think in this terms of design. It motivates us to care about polymers and colloids and emulsions and a whole range of things. This paper focused on that microstructural level of fluid physics, but just for one of those key rheological properties. And so I'm reminding you with the images on the left what those are: the viscoelasticity, shear thinning, extensional thickening, and the shear normal stresses. And we had just focused on one, so you can easily imagine that you could do something similar, or we as a community could move forward by doing something similar for how to design other things, like designing the viscoelasticity or how much extensional thickening. Or a nice area that's gotten a lot of activity recently is high volume fraction athermal particulate systems, things that show shear thickening. And of course, we're first trying to understand where that arises from in the first place. But if there are multiple mechanisms, this makes it a very interesting design problem if we wanted to create or negate shear thickening as well. So this focus on microstructural, but there are also continuum level physics questions. For example, this paper said nothing about how do you find the property that you really want to target. It mentioned a few that would be useful. And is it even possible to identify what you want independent of the microstructure you'll use to achieve it? For example, can you identify what yield stress is required independent of using polymers or colloids to achieve it? This may feel normal or natural in our fluid mechanics community because this is often how we look at the world. For example, when we think about dimensionless groups, we think about continuum level properties that's completely agnostic to the structure. We assume, for example, there is a viscosity and it does come from some chemical structure, but we don't care what that is. As long as we know the viscosity, we can make progress. And that's the spirit of this next portion of the talk that I want to discuss is thinking about the dimensionless groups for understanding complex behavior as a way of identifying design targets that are agnostic to the underlying structure. For this, we're very much motivated by the fire suppression application. As you know, this is a very important thing worldwide, from Australia a year or two ago and now, but also now in the US, especially in California, but across the West. There are many other places struggling from wildfires. And one mechanism to help put them out with a lower volume of water is to make that water non-Newtonian. You'll see in the video I'm playing here, water is dripping down onto a burning piece of solid fuel on the left. It's camphor that's burning. It hits and it splashes away under these conditions. And on the right, I'm dropping what's mostly water and just 0.1% by weight additive to turn it into a complex fluid that has this dramatic shear thinning property. And you see as time goes on, that liquid is able to act something like a liquid blanket to coat and cover the surface, isolating the fuel from the oxygen and even taking away the heat because it's water-based. So we asked ourselves, this is of course very motivating, but we asked, do we really understand how to even predict if the droplet will impact and stay versus splashing away and being ejected from the impact site? And that's what this thread of work was about. That was started with me with Brendan Blackwell, who's now a postdoc at Northwestern University, with Michelle Driscoll, who's in our DFD community, and a current PhD student, Samya Sen, who's been continuing this work forward. We've looked at this in diverse, complicated geometries. On the left, you see a droplet impacting screens. This was inspired by thinking about droplets in a wildland fire scenario impacting the canopy, where they impact something that has a porosity, and they might then come down and coat multiple layers or multiple distributions within that canopy structure. This is, of course, very simplified to have discrete layers of controlled porosity, but it was a start to show that if you just have water, most of it goes through. If you create a fluid that has a too much concentration, the yield stress is too high, it actually just gets stuck at the top. And there's some Goldilocks condition in between that allows you to impact and coat throughout. This is a high dimensional parameter space, like many of these droplet impact scenarios are in our fluid mechanics community. Using our typical approach in fluid mechanics, we asked, is there a way to identify a dimensionless group that can simplify and project the complexity into a single criteria? So long story short, the answer is yes. It's related to the equation on the bottom right. It ends up being a comparison of inertial effects, the incoming momentum of that droplet, compared to the total dissipative effect. But with one important modification, it's not just a comparison of characteristic stresses, it really is a comparison of characteristic forces, and one has to consider the different geometric length scales that are giving you the true ratio of these effects. We see this all the time in fluid mechanics, though here we weren't starting from a governing equation that made it reveal that it was a comparison of these length scales. It required hypothesizing and postulating what that comparison should be. So it looks like the comparison of stresses, but then modulated by this ratio of the diameter of the drop divided by the thickness of any existing layer. For example, from an initial drop that lands, that thickness plays an important role. We asked, can we really identify these criteria independent of the microstructure? And one microstructure we looked at was a clay particle suspension. These are videos showing you output from the experimental setup. Everything's the same here except for the impacting velocity. So for fire suppression, it's still not clear what you would want. Would you want impact that sticks like on the left, or would you want it to splash away and splatter around your scenario? And we don't know the answer to that yet. We started with the more fundamental question. Let's assume you do know where you want to be. How do you understand where you're going to be in terms of the properties? So we characterize the impact type behaviors with this key that's shown on the left, ranging from just a lump that impacts at very low incoming momentum compared to a splash where the impacting material is distributed very far and breaks up into many pieces. We did not look carefully or have significant interest yet in the initial crown splash that occurred. We were looking at the larger scale structures here. And in the end, across the huge range of experimental conditions, it was a 4-parameter space that we were exploring with hundreds and hundreds of different conditions and combinations. It turned out that this dimensionless group works exceedingly well at organizing that space and identifying these transitions between when you're going to stick and when you're going to splash or eject material away. When you do this for another material, this is the real question. What if the formulation was complicated? Is it even going to work with the same dimensionless group? And what we see is that, yes, it essentially works with the same dimensionless group. It separates the regimes. But what you do see is a little shift, or maybe a big shift, depending on how you interpret it, in the critical value for transitioning from one regime to the other. And so there is something subtle going on here that the steady state properties that are used in this dimensionless group are not capturing. Maybe that's not surprising. Why should steady state flow properties in shear be enough to predict what's going to happen? It's remarkable that they predict as much as they do, but they can't get this difference in what the critical value is between these two very different microstructures. I'll move those plots to the bottom and remind us that all of this is really focused on the shear thinning phenomena. It doesn't account for any viscoelasticity, nor extensional thickening, nor the shear normal stresses, nor thixotropy, what some of us call the fifth key phenomena. But it does enable design in a way that complex fluids enable design, because you can really control the relative values of some of these properties of what goes into your fluid. I list some of the caveats here of where our work continues to go. Samya will be presenting at this conference. His talk is Z03.08. If you're interested, you can go check that out and already start commenting on his talk over there. But for the talk here, I just want to ask, what if the properties were really more complex? This is in some way a lucky, simple result where I only care about constants that appear in the denominator of this number. What about the shapes of the rheological functions, like the shape of the shear thinning or the shape of the viscoelasticity? And we started asking some questions like that. And we started with the viscoelasticity because this is a very universal place to start with linear viscoelasticity. I'm showing the equation at the top where we substitute in for the stress tensor linear viscoelastic Boltzmann superposition as general as we can get for an incompressible isotropic viscoelastic liquid. And we ask, is there any way to start designing the shape of the kernel function to achieve diverse objectives? One interesting thing is you cannot independently design any rheological functions you want. For example, if you're familiar with viscoelastic moduli, you can't just draw shapes of each of them that you'd like to achieve because these are interconnected. They're all interconnected because of this kernel function here. So we've considered example scenarios like a quarter car suspension, where there's a road profile that inputs a diverse range of frequencies into a sprung mass system, and ask what optimal viscoelasticity can achieve these objectives. This itself is not an obvious problem statement because there's not just a single objective. There are multiple objectives. In this case, it might be the combination of handling and comfort, which usually compete against each other. But in framing it this way, it's motivated us to identify all of these important questions like, how do you represent the model? Do you represent it as discrete spectra or continuous spectra? Where we started leaning towards continuous spectra because we think that these end up representing more of the physically realizable systems that can actually achieve this viscoelastic behavior. In thinking about these inverse problems for optimizing the shapes of curves, we thought about how it relates to existing activity in engineering design, where you really are designing the shapes of curves. And here's a fluid mechanics scenario where that's true, where we were thinking about something that looks a lot like a thrust bearing, where I have two plates. One is shaped and textured in a certain way. The other is spinning in rotation, and we ask how much thrust is generated as a function of how much torque is required to make it spin. And you know this from your understanding of hydrodynamic full film lubrication bearings, that it matters what shapes you have. Here, we wanted to be very arbitrary to ask how arbitrary can the shape be to really generate the design performance that we want. We started this with Newtonian fluids because this was a starting point before we designed both the shape of the surface and the rheology of the fluid that's inside, which actually had a huge benefit. So Newtonian fluids are good. The viscous effects generate pressures inside that cause lift, and you see a nice balance or trade-off between the amount of torque, that's the x-axis, and the amount of normal thrust that's generated here. We expanded that design problem to start including non-Newtonian fluids. Here I'm just changing the sigma to a tau because that's the notation we used in this particular paper. And you realize there are all of these questions such as which of these models should I use? Which do I believe for my material? But if I want to be totally agnostic to my approach of my formulation, do I need to look at all of the models? And so we're right now wrestling with how to organize the choice of models for the purpose of design. Which ones are general, which ones are not? We were able to achieve some success here. One interesting result, as I'll point out, again, there's this trade-off in the design space between generating a normal force and requiring a certain power input to the torque. You can generate more normal force at the cost of requiring more torque. The utopia point, as they call it, better performance is up and to the left. And this front that you see with all of the colored symbols is called the Pareto set or the Pareto front. As you go along the Pareto front, you see a trade-off between different shapes of the geometries that's shown with these colored sectors here that shows topography of the height of the surface. And on the left, you see for each geometry, there's a particular, for example, I'll circle A here, there's a particular rheological signature you would like to have that's most optimal, paired and coupled with the particular shape of the surface. And as you explore around this Pareto front and go back and forth, you explore around where in the rheological parameter space and where in the surface texture parameter space you really want to be. So we're not solving the problem because the final problem really decides on your application and where along that Pareto front you'd like to be, for example, considering other multi-objective questions like cost of manufacturing, et cetera. So this is all on really thinking about shapes of curves and things. But as I said, it brings up questions about the modeling. The first question that comes from the materials chemists is, okay, this is great, but I don't even know if I can achieve that target. You're using too much design freedom because you're not constraining it by what's really possible. On the other hand, I would say the more interesting thing is that some of these models are too restrictive because there's rheological behavior that exists outside of the paradigms of current tensorial continuum level models. And that motivates what's next here with our work related to 3D printing. This is again the work of Gareth, working with Brittany Rouzan, who is a recent graduate from Illinois as well in the chemistry department. Brittany was really excellent at the materials chemistry side of this project. Gareth was the guru related to designing the rheology. So we started asking ourselves, what's the right rheology, or what rheology is good for 3D printing? And you can find in the literature, and it's obvious from the video, you want to be shear thinning, you want a particular yield stress, etc. But what had not really been considered at all is this idea of superposing or adding in this other key phenomena of extensional thickening. Many of the model materials that we study academically that are shear thinning yield stress fluids do not show any extensional thickening that would appear in a qualitative sense like in a video. We had reason to be thinking about that because Gareth had just written a paper on this new paradigm, this idea that most academically studied materials, represented like this clay suspension of bentonite here, they show a yield stress, they retain their shape at low stress, but when you try to extend them, they break at around that level of extension. Whereas real materials, like we're just showing a printing resin, and for the extreme, something you can connect to, bubblegum as well, which has a yield stress and it has very high extensibility. So this definitely exists, but there weren't model materials to really study this range of yield stress and extensibility. Gareth formulated a material. He used his design framing that I talked about, considering lots of different possible ways to achieve the yield stress, many different possible ways to achieve the extensional thickening. In this case, he's using a transient network of something that's not a very large molecular weight. It's about 100,000. Usually we think about millions of molecular weight for things that show obvious extensional thickening. And he was able to achieve a range of properties that was relevant to these real materials. And we wondered if this would be useful in the context of 3D printing. So Gareth formulated a different material that was relevant for the printing. Here I'm going to show videos of extensional tests across a range of the formulation space. In this case, just varying the molecular weight of the polymeric additive. It's added into an emulsion. It's an oil and water emulsion. And you see we've got a sweet spot where we get dramatic extensional thickening here with the 5 million molecular weight. These are all done at the same weight fraction, but a different molecular weight. And so the dimensionless concentration of C over C star is changing. The Weisenberg number is changing. For those of you who might be asking, we use the same extensional rate in all of these tests, even though obviously the viscoelastic relaxation time is expected to be changing. But this was one way to just show how different the material might act when you're really 3D printing at a particular velocity. And that's where it showed great promise. In fact, we could print things that couldn't be printed otherwise, and we could print faster than we could print otherwise. These other materials suffered from breaking. They were much more brittle compared to how stretchy and ductile and flowable these other materials were. So you might be able to identify, in this case, some sort of design target for the extensibility that doesn't really care about what the microstructure is, perhaps. There may be other ways to achieve the same continuum level behavior. You're not done just because you can print. In this world, you have to transform chemically your material. At the bottom, I'll show two videos. The left is the 3D printed material that's a lot like cake frosting. And if you try to have it carry any meaningful weight at all, you just destroy the entire system. Whereas on the right, we've transformed this chemically to be much more of an elastomer. The printing process takes some time. And so when the students did this test of applying a finite load, it was a little traumatic to see the video on the left where everything is just immediately crushed. But on the right, we had hope. we can change this particular oil and water emulsion into an elastomeric material that bounces back completely from that very large deformation at the beginning of the video there. That's, of course, non-trivial, and that makes me very thankful for our chemistry collaborators to make things like this happen. And the story touches on both that material level chemistry and the continuum level rheology and fluid mechanics. Even though we weren't doing simulations to identify what properties do we want, I don't know if we really could have succeeded there, because it was a shift in a conceptual model of how these materials behave in terms of what we might stick into this governing behavior for the stress tensor. So to start to wrap things up, we've got a vision for where this can go into the future. There are many reasons to be inspired. A lot of other properties. I didn't really mention much about thixotropy, but thixotropy is another key phenomena that's very interesting. We're still understanding the science, and as we develop the science and that analysis side, we'll be able to develop more of the design side of being able to control this. But keeping the design in mind helps us to organize our research activities. I'll just say that we're really looking for more intuition here also, and other ways to pose the mathematical problem. I'll just show a couple more examples, just one slide, touch points on some things. This gives me an excuse to mention the local chair, John Friends. He and I collaborated on this paper with student Jaekwon Kim. To think about using adjoint-based sensitivity methods to say, how does some quantity of interests, for example, here I have a sphere that's inside of a thixotropic shear thinning fluid. How does the drag on that sphere depend on the rheology, but not just the rheology being the same everywhere, but you have this amazing way in this mathematical framework to ask, how does my drag depend on the rheology in every point in space, which is really cool, because I think it motivates other paradigms of thinking about the design. Like, if local changes matter, maybe you can think about locally heating or locally changing in some other ways for achieving your objective. Rebecca's been thinking a lot about intuition. I think if we're going to teach undergraduates how to design with these things, we need to give them very quick intuition. Here's, for example, putting a range of viscoelastic materials on the different perspectives in terms of both fluids and solids of where the viscosity and the elastic modulus would lie. And finally, I'll just point out Yilin Wang, who's a current PhD student working with me here at Illinois, also has a talk at DFD. She's thinking about the design for these redox flow battery systems, where there's a very interesting trade-off in how you achieve the transport properties you need to get the energy density that you want. So you want high concentrations of molecules that are electrochemically able to store energy, but you have to deal with this trade-off. And at what level can we have predictive models versus these other paradigm shifting approaches? So I point you to her talk there if that sounds interesting. I'll just wrap up by saying thank you to the wonderful community that I have here at Illinois. It's been an amazingly, and continues to be amazingly interdisciplinary to interact across chemistry, material science, and to find excellent people who think deeply, who are also wonderful human beings. And speaking of wonderful human beings, I'll end with this acknowledgement of the people who you've seen highlighted. The students are on the left, a couple images of the key faculty colleagues and collaborators that have been influential, including Gareth and Pecco also, who was influential in seeding some of these ideas a while back when I was a student with them. So thank you all for your time.
Great. Thank you, Randy. Can you hear me okay?
Yeah, loud and clear.
Wonderful. Excellent. There's a number of questions in the Q&A, and I will read a couple of them to you. We've got about 5 minutes or so to go. First one, going back to the first case study on the impacting yield stress material. The question from Paul Sagnick is, how does the droplet size, how did you vary that? And does the addition of additives change the droplet size? So maybe you can say a little bit about controlling droplet size. Yeah,
that's a great question. So that was somewhere around this slide 15-ish here. Yeah, great. So let me show Sam's nice videos on slide 17. So the droplet size is tricky because if you've ever tried to drip a viscoplastic fluid, you out of your toothpaste tube, for example, you know that it doesn't form a sphere at every length scale because the yield stress resists the effects of surface tension that are trying to form a minimal surface. There's a nice dimensionless group that compares those two things. All of our droplets here are large enough that surface tension doesn't have the strength to form this into spheres. And so we've made something that we colloquially call the drop chopper that quickly chops the shape of a drop so that it can fall down in an approximately spherical shape. It requires some hydrophobic, super hydrophobic coating on those surfaces so that when we move quickly, it doesn't stick. It's not perfect, but it's pretty good, and it's definitely better than squeezing out a cylinder and chopping off different volumes that then appear as disks, because those edges throw things off more than the inconsistencies we have here.
Right. Great, thank you. Another question on the same topic from Kashitzis Gupta a question is, are there any environmental effects of this additive? Is it biocompatible? Is it going to be safe to spray forests with this additive?
Yeah. So let's see, that was back here, I think. So this image in the bottom left, the companies who make these things name themselves things like Earth Clean Corporation. That's the attribution for this particular image here. So I'll say it's forefront on their minds that this is one of the design objectives as well. Our work so far has not tried to ask that, but our work to identify material formulation agnostic targets, I think, enables them to think creatively about how best to achieve the rheology that's really needed. But of course, it becomes this multi-objective optimization where you have to factor in the health hazards. Things that they added in there. There are ways to make this biocompatible. The U.S. Forest Service has a list of tested things that they've proven out to be okay within the standards that they've put in place.
Wonderful. I think we've got time for maybe two more questions. There's a number of other questions, but I'm going to jump forward to cover some of the other parts of the talks. There's a question from Georgios Katsikis. He says, in the slides with the 2-panel videos, how do you transform into elastic solid? Before you crushed this student's lovely 3D print. So is it photopolymerized or thermally cured?
Well, I'll have to.
And if yes, you get an undesired change in dimensions due to residual stress, was a question.
Oh, great question. We will, to the extent that we've looked, we haven't been upset with any residual changes in the dimensions, but dimensional consistency certainly is an issue with any manufacturing process. This happens to be a 2-step process. It requires both a chemical and a thermal annealing step. Essentially, the chemists suggest that there's some remnant material that allows the silicone oil to cross-link, to initiate a cross-linking reaction. And to my mind's eye, magically, these dispersed droplets of oil find a way to coalesce enough to form a continuous network. It doesn't look like it's just a bunch of little spherical elastomers. It really looks like it's a continuum of elastomer that results. And in my mind's eye, again, I said it's kind of magical how Brittany was able to make that happen.
Wonderful. And I think we'll pick one last question from the very end by Nathan Rungan. Says, great talk and gets you thinking about material nature that we approximate. And the question is, what are the effects of temperature and maybe hydrophobic or hydrophilicity being added to the design objective?
These are great. There's probably something deeper lurking behind that question, maybe even a specific design objective you have that I won't be able to speak to, but it's a wide open space. Like I said, a small step beyond Newtonian explodes the range of possibilities. And you're rightly pointing out there are even other things beyond the fluid properties that may be playing a role, like how the fluid, or beyond the continuum fluid properties of how the fluid, for example, interacts with its surrounding surfaces. I'll maybe point out with, for example, the fire suppression, you do also care about how wetting the liquid is to the surrounding materials, which is not a rheological property as such.
Wonderful. Well, I make it 4:07 and the next session begins at 4:10. So this would be normally where the TV signs start going black and saying next session starts. So I think we should all thank Randy virtually. We can't share a clap, but just let's thank Randy a lot and encourage everyone else who had questions that I didn't have a chance to answer to reach out directly to him. But I think we can stick around here for a few more minutes while we're live. I'm sure I'll get told by a moderator if that's not the case. And so I will ask one more question from Rosanna Pasquino that asks, did you try creep experiments on the chemical design materials to quantify the loading experiments?
Yes, I think you're maybe, Rosanna, referring to the image that's shown up here. We did do creep on the left. This is a classic way that we like to characterize the yield stress fluids because we can't always get the flow curves. For these, we are able to get the flow curves. I didn't mention them, but I had them on a slide a couple back here. Let me just show you underneath all of this filament stretching. On the right, we were able to make this material flow, and so we could get to steady state. But oftentimes in this world of yield stress fluids, we're doing creep tests because we can't quite get to steady state. And to characterize the yield stress, we need to find other ways to do it. If you do look at the creep compliance, you're also looking for, how long might you wait until you see creep and these materials sag that you've printed. We haven't looked at very, very long times, but suffice to say that from the time that we print it to the time that we chemically transform it, it's certainly acting essentially like a solid material here.
Wonderful. So lots of comments flooding in saying thanks for an interesting talk. Thank you all for attending. Here's an interesting, very open question that came in earlier on that I'll ask from Konstantin Leonov. It says, question is a little bit off the topic, but could you tell me something about complex fluids for atomic energy, e.g. fluids with interesting thermal properties for fuel elements in a reactor? There's a new design topic.
It sounds like a lead into a proposal from whoever's asking that question. That's great. I don't know anything about that area, so I don't know if I could tell you anything, except I've heard the word thixotropy thrown around with particulate-based systems that show up in the world of nuclear applications. But that's the extent I can touch on. I'm sure there's probably something exciting there to figure out.
Right. Excellent. Okay, well, I'm sure we could carry on forever. Do you want to carry on, Randy, or do we stop and let people go to the next session? It's exactly 4:10 now. So
I think in the spirit of fairness that our community has, let's encourage everyone to wrap up and go forth and hang out with the other sessions that everybody would like to be interacting with.
Wonderful. Well, thank you once again for a great Sunday afternoon, and please reach out to Randy directly for additional questions. But thanks, everyone. I'm going to end the webinar.
Thanks, everybody.
All right, I ended it. Oh, I'm ending it in 7/6. Well, I think that went